Alright guys, so today we are going to be doing acid catalyzed dehydration of cyclohexanol, which is this species right here. Our acid that we'll be using today is going to be sulfuric acid, which is H2SO4, to form cyclohexene, water, and then regenerate our sulfuric acid. So with respect to sulfuric acid, this reaction is completely catalytic. You can also notice that in each step of our mechanism here, we have an equilibrium forming. So it's important to know how we can manage our equilibriums so that we can favor our alkene product. The mechanism goes as follows. The lone pairs on one of the oxygens will grab a hydrogen, proton, from our sulfuric acid. This will then form this hydronium intermediate here. You see this purple proton is from our sulfuric acid. We generate a positive orbital charge on our hydroxyl group. We then have this alpha proton shown in red here. Our conjugate base of our acid will then come and deprotonate here. This will generate our alkene, water, and regenerate our sulfuric acid. This reaction is called a dehydration because we're actually generating water, and it's coming from our reagent. Hence, a dehydration reaction occurred because we lost the equivalent of water.
Okay, so after we make our product, we got to go on to characterization. We got to be able to say we made our stuff. So the first thing we're going to do is IR, and the second thing we're going to do is a bromine test. So with the IR test, we're going to do, we have our starting material, which is cyclohexanol, and then we have our product, which is cyclohexene. So there are two significant bands for each product and starting material. So in the starting material, you have the band at 3,300 for the alcohol, and then you also will have a sharp peak at around 2,900 for sp2 hydrogens. So if you have these two hydrogens here, or at any other position on the ring, that's what this band is going to show. Now when you move to the product, cyclohexene, you will also have them sp3 hybridized carbons, but you're also going to have the sp2 hybridized alkene. So for this hydrogen, you're going to get in a band a little bit higher, around 3,000 wave numbers, and then for your sp3 hybridized carbon, you're going to see around 1650. It might not be easy to see, but we'll see after we get the spectrum. So that's going to be our first way to characterize our product. So the second way is going to be the bromine test. So how this works is we take elemental bromine in solution, and what's going to happen is the alkene acts as a nucleophile. It comes, and electrons grab a bromine. The bond between the two bromine atoms breaks and moves to one bromine, and then you go down to this intermediate with a brominium ion. So when you make this bromide ion here, it's going to come back and add as a nucleophile, and then you're going to get a disubstituted bromine complex. And this is going to be clear, whereas this solution is an orange or red. So that's how we're going to have two different types of characterization for our product. So we're going to move on to the lab now. Okay, so before we get the lab started, I just wanted to explain our setup. So we're going to be using a distillation setup to run the reaction today. So what we're going to start out by doing is filling this 100 milliliter round bottom flask with your sulfuric acid and cyclohexanol. So this is sitting in a heating mantle with all your blocks, just like you used in previous labs. So this is plugged in to a regulator over here, which is plugged into the wall. So that's how we're going to control the heat. So you have your three-way adapter hooked into your flask. Your adapter has your red fitment guy that holds your little thermometer. So you do want to note that the height that the thermometer is in this three-way adapter is important. You want it to be about halfway through or maybe 2/3 of the way down, just so you get accurate temperature readings. So off your three-way adapter, we have a condenser. So again, same idea as what you used before in previous labs. We have the water coming from the faucet going into the bottom adapter right here. So water feeds in, comes up through, leaves the top, and then goes back into the sink. And you only need a small trickle of water just to keep your condenser cold. After the condenser, we have this little vacuum adapter that hooks onto our flask here. So while you're running the reaction, this is going to evaporate, condense, and then your product will fall into here. And we'll have some further steps to go for after that.
Okay, so our first step is going to be adding our cyclohexanol to our round bottom flask. This is 10 milliliters worth. And next we're going to add this concentrated sulfuric acid. This is 18 molar. Now the procedure says to add 1 milliliter. We are going to add approximately 10 drops. This will be equivalent to 1 milliliter. Slowly, drop-wise, while also swirling the container at the same time. So, we're going to put in 1-ish drop at a time, swirl around for a little bit, make sure everything's all evenly distributed. And we're just going to keep adding until 10 drops have been fully added. Once the 10 drops have been added, we will then continue swirling this for 5 to 10 minutes. Okay, so now we have been swirling for 5 minutes. What we have done is we put a few boiling chips inside of our reaction flask right here. What we want to do is keep our temperature below 100 degrees. And we also want to keep our receiving flask nice and cool. We've done so by adding an ice bath in here. Now, next thing we're going to do is we're going to be looking out for when our first drop comes into our receiving flask. And we're going to record that temperature, and we're also going to record the temperature at which we have stopped our reaction. So we will come back to you when that is completed.
Okay, so we just got our first drops coming through. I know it's hard to see through the video, it's even hard to really see in person, but we are getting some condensation up in here. So our temperature right now is just approaching 80. We went about to 90 or so, but then we took it off the heat because we didn't want it to get too hot. So I'd say the first recording for temperature would be about 85 degrees for the first drop. And now we're gonna let it sit here and cook for a while, and we'll come back to you guys after we get the rest of the stuff to evaporate. Okay, so after about a half hour of the distillation, we've finished. We've taken the flask off the heat. It's cooled down for about 10 minutes now. You can notice that the leftover stuff we have in there has like a kind of like an amber brown hue to it. So that would be something to note in your in-lab, hint, hint. And then we go over, see a little bit of condensation in here left over. And this is how much volume we have left. So you can see it's a little bit cloudy. So there might be some impurities in there, like water or other stuff. Should be a clear solution, but we're gonna take care of that pretty soon with an extraction. So that's how we ended up after our distillation, and our final temperature was 85 degrees Celsius.
So now we have poured our crude reaction material into our separatory funnel. This was in our receiving flask. So now you can see that 2 layers have formed, this top organic layer and the bottom aqueous layer. So now we're just going to quickly separate that into a beaker. Just like so. And now we're going to perform our first wash. Our first wash is done with a 10% solution of sodium carbonate. This is just going to be emptied into here, like so. And then we are going to stop this. We're going to take it out. We're going to invert it, open, then slightly shake, venting frequently until the layers have been sufficiently mixed together and all the acid has been neutralized. So once we feel like we've done a good enough job, we're going to put it back in here, take off our cap, and we're going to wait for the layers to separate. So now the layers have been separated, we're now going to separate out the bottom layer. So by opening this up, just like so. And now we're going to repeat this process for 5 milliliters of water and another 5 milliliters of a saturated brine solution.
Okay, so now the separatory funnel is empty, This beaker contains all of our aqueous washes, so containing your brine or your sodium bicarbonate, anything you used to wash your cyclohexene. Okay, so we removed what was left of the cyclohexene and put it into this beaker, and what you see in here is the calcium chloride drying agent. So even though you remove the water from here when you did your separation, you're still going to have residual water left inside your cyclohexene. So the calcium chloride is supposed to absorb most of that water as acting as a drying agent. So I know it says in the procedure to use a vial, but we just used a beaker. There's really no difference. You just need a little container to hold it in there. So we're going to let this dry for a few minutes, and then we're going to move to our second distillation setup.
So now we have dried our crude reaction mixture over some anhydrous calcium chloride. We have transferred it over to this 25 milliliter flask. This one is not pre-weighed. We're just getting ready to start heating it up. Before we heat it up, of course, we'll add in some boiling chips. We want to keep our temperature somewhere between 80 and 85 degrees. And our fractions will be collected into this pre-weighed flask over here. This is going to be cooled on ice bath, once again, to limit evaporation of our product. And we will come back to you guys when we have collected everything. So here we are at the conclusion of our second distillation. You can see here that we did not distill the dryness. There's still some remaining liquid in the reaction flask. Our temperature didn't varied from 78 to 87 degrees Celsius. Over here you can see our purified reaction mixture. Still being cooled in ice bath to limit evaporation loss. So now that we have completed this step, we're going to move on to our characterization tests. In this vial here, we have several drops of our product. In this vial here, we have our bromine mixture dissolved in DCM. So what we're going to do is we're going to take several drops of this stuff out. So you'll notice how it's a nice dark red color. I'm going to put several drops into there. Close this up because it's very friendly to work with. And you'll see, even though we've added several drops of our bromine mixture, we still have a completely crystal clear, not orange, solution, indicating that we have an alkene present.
Okay, so as our second form of characterization of our product, we have IRs. So I'll upload documents that have these scans, so you can also look at these as still images for your post-lab report, so you can characterize all your stuff. So just to go over them quickly, so this is a IR pure cyclohexanol. This is from the bottle that we used for our starting material. So you can see your OH peak right here, and then your your SP3 peaks right here. You move down to cyclohexene, which just is pure stuff that we have from a commercial bottle. This isn't from a reaction mixture. This is just more as a baseline for you to be able to compare your actual crude product that we made to pure stuff that you know what the spectrum actually is. It can be verified. So the big part you could take from this is this little peak right here at 3022 wave numbers. It indicates the sp2 hybridized CH bond, so it's alkene. So then if we go over to the IR of our final product, you can see some similarities here. I won't go through all of these, as you guys, it's part of your assignment to go through and characterize with your spectra. So one thing I will note is there is a little lump right here. So that would be something to touch on in your lab reports. This isn't a peak, it wasn't picked out, and there's not a value, but I would talk about what this might be. Okay, here is a still image of our tare weight and the mass of the flask with cyclohexene. So this is just for your information for your calculations. So to find your yield, you just subtract the mass of the cyclohexene, mass of the flask with cyclohexene from the tare weight that's right here. So that's all you need.